Hello everyone. This is kind of the first video I'm ever making, so hopefully you enjoy it. It's not meant to be like an enjoyable thing, but it's essentially on my mathematics essay for the Tom Rocks Maths essay competition. And I really just wanted to go through it because there were some problems that I had that I thought maybe if I dig into it further, I'll kind of get some responses on YouTube and help on YouTube, because there's kind of a conceptual gap and there's not really help for it in my, just day to day at school or anything like that. So I just wanted to ask for help. It's kind of a plead for help, but it's also a look at my essay. Obviously, there's some pre-reading you can look at here. It's called Let's Break Stuff. The premise behind that is you just doing stuff in mathematics with the idea of breaking it, kind of. Not really, it's not really a good description, but that's kind of the idea that I'm building towards here. So I start by just explaining why I like breaking stuff and the kind of things that happen when I break stuff, and then we go into kind of what I'm breaking today. So today I'm going to be breaking the geometric series equation, and I'll just show you that now. So we start with rule number 1 of breaking stuff. I broke them up into 3 or 4 rules. I think it was 3 rules. It's been quite a while since I looked at this essay, just because I've been so busy and stuff like that. So then I start off with saying, okay, take the following geometric series, and I just this video is not meant to really explain a lot. It's more of a plead for help, so I'm sorry if I don't really explain what I'm doing here. If you do follow along, that's great. But yeah, so I start off by listing the geometric series. I think 139. So I list the geometric series here, and I try to explain what a geometric sequence is first, and then I explain a geometric series, the concept here. Geometric series simply is when you get a geometric sequence, which is just a pattern of multiplying a certain ratio. So say one times 3, so every term you times by 3, so 1 times 3, 3, right? That's your next term. Then you times by 3 again, you get 9. Then you times by 3 again, you get 27. That kind of thing. And then a geometric series is just you adding up all those. Instead of having term by term by term, you add up all those terms to get a value. And that value is associated with how many terms up to that part of your series, kind of, that you've added up. Hopefully that makes sense. Then over here, I explain just what the geometric series equation is. I won't go into how you solve that, but essentially you can find some videos on YouTube. I'll link some videos on YouTube. Probably 3 Blue 1 Brown has some videos on there which would help you with that. So yeah, we just go into a divergent and convergent series, things like this, and just a further explanation of that. I'm sorry if I feel it's a bit confusing at this point. Then I'm just trying to find it. Okay, yeah. So I'm just find where I start. So let's find the part here. Okay, sorry there's not much prep work into this video. It's kind of like an impulse thing. Yeah. Then I say, let's begin with a simple observation. We start with difference of 2 squares, and it's just the property of x squared minus a squared is equal to x minus a, x plus a. And you can get that by just simplifying this. You say x squared, and then you'd have plus xa, and then you have minus xa here, so those cancel. And then if you have minus a squared over there, and that shows this kind of simplified equation there. So I really just expanded here just to show the principle of what I'm doing, and apply that similar concept over here, which x minus a, and you'd say x to the half times x to the half. By law of exponents, those would add up, so it'd be a half plus a half to make 1. So you'd have x to the 1, which is just x, and then the same principle of dots would apply there, and then for a here you'd have the same concept, and it'll multiply there. Then after that, I go into the geometric series equation, and say a r to the n minus 1 over r minus 1, which is just the series equation normally. That's fine. And the whole purpose of this essay is expanding this by using this principle up here. So that's the core of this essay. So I do that here, and I say a times r to the n over 2 minus 1. And the reason I say minus 1 there is because if you expand this, or simplify it, let me say, and we just did this once, we'd say, okay, r to the n over 2 times r to the n over 2 is just r to the n, right? It'd be n over 2 plus n over 2, which is just n. Then you have over here, you have r to the n over 2 plus 1, that's r to the n over 2. And then you have minus 1 times r to the n over 2, so those cancel, right? And then you have minus 1 plus 1, those multiply together, make minus 1, and hence you get the same kind of answer here, right, over r minus 1. So we can clearly see that there's, as long as you have a kind of normal value, or not normal value, just some variable, and then you have to the anything, to the 7, to the 8, you can kind of use difference of two squares to expand anything further, right? If it has a minus 1 or a minus whatever value you have. Minus 1 happens to work here to get plus 1 minus 1, which is what I go into later on. Yeah, so in step 2, I essentially say, okay, over here we can do it once, right? Over here we can do it once here, but we're not limited to how much we can split this. So we can have r to the n over 4 times r to the n over 4. Well, no, let me preface and say you can have r to the n over 4 minus 1 times, so in brackets here, times r to the n over 4 plus 1, right? And then essentially I'm saying you can repeat that process by halving and halving and halving repeatedly, and expanding this kind of minus 1 bracket continuously. And I define that as k, and I'm saying k here, introducing a new variable, which is the confusing part. Now, how do I deal with this? How do I work with this? I'm introducing a new variable into the equation. Is it a completely different equation? In my mind, it should be the same, because you can multiply everything out, or simplify everything to get the same r to the n minus 1 we started off with here. So it should work in my mind, but we'll get into that a bit later. So I essentially do that, and I do that k times. So I continuously use difference of dots this part here repeatedly for an infinite amount of times. I call it anyway. I don't know if I can do that, but I just did it. You have that there. So you do that repeatedly, and you have r to the n over 2 to the k minus 1 times r to the n over 2 to the k plus 1, which just represents me doing it an infinite amount of times and having a infinite kind of leftover. I call these leftover terms, but I have an infinite amount of them, and I stop at k. Not stop, but kind of like infinitely far away, but I'll have an infinite leftover value or bracket kind of. So I do that. But r minus 1 is just I just left this here. We'll get to that later. And then I just want to get to yeah, I think we'll just get to this part here. So I call this PK. So this, let me just show you here. This part here I call PK, right? Leave the A here. Keep it in the back of your mind. It's not really important. We'll deal with that later. It's a constant value. And you might ask me, where am I going with this? Why am I doing this? I don't know. Just hang along for the ride, I guess. So I call that top value PK. And then I just show it like this. The colors makes it a bit easier to see, but I know that it's a bit difficult. But yeah, that just comes from there, so there's no problem with that. So now we gotta look at n over 2 to the k, and big problem. Let me show you this. Okay, so you have limit as n approaches infinity, which is fine, I guess, maybe. I'm just saying you can put in any number here. Infinity, I don't know if infinity accounts for smaller numbers, so negative infinity, or if it accounts for, well, it's n, so it's a positive number. Actually, I don't have to talk about that. But I don't know if it accounts for smaller values, and that's something I'll talk about later on. I think just a bit further on here. In k, I defined as infinite, so that's my definition. Doing an infinite amount of time, so it's an infinite number, kind of an infinite k value. So that I have no problem with it. The k, the n to infinity, that was just the 50-50 attempt to be like, okay, let this apply to most values of n. And by saying to the infinity, hopefully, there's not really any rigorous proof of this, but I'm hopefully like accounting for all possible positive constants of n, positive integers of n, kind of. So I do that here, and I say the limit as n approaches infinity outside here. So I'm evaluating k to infinity first, and then n to infinity, which apparently means a lot, right? Evaluating them separately by order is very important, and I don't have the skills to do that. Someone could help me in the comments, or if anyone watches this, I don't know, if you could help me understand how I evaluate infinities per se. So then let me go here. So I'm just checking if the recording is working. Okay. So I do this here. I say the limit is k approaches infinity. As I said, don't know if I can do this. Just doing it. And what I do is I'm a bit more smarter or succinct with how I use mathematical notation now, because we did natural log, but here it was just plug and chug. Hopefully it'll work. So I said n over 2 to the k. So I remember I used L'Hopital's rule here. No, that's what I did here. I used L'Hopital's rule. And essentially what I did was like, okay, I need to somehow evaluate n over 2 to the k. What number does that approach? What does that look like? N over 2 to the k, by the way, just to remind you, comes from this, right? Comes from this and this. But we're specifically talking about this one here, this bracket here, this n over 2 to the k. N over 2 to the k. And I said, L'Hopital's rule, this is a constant n at this point, because I'm evaluating k then n, so n is a constant at this point. It definitely is a constant. No matter what I pick for n, it will be a constant, because n is a value I plug in, which might have broken the logic between n being any number, you allowing n to be any number, and it being a constant, but right. So it's constant here. We differentiate the top, it just becomes 1. Then we differentiate the bottom, and now I'm looking at this with you. We're looking at it together. I have not prepped this video, so we're evaluating this together. 2 to the k, yeah. yeah, this looks fine to me. The natural logarithm 2 to the k times the natural logarithm of 2. Yeah. Yeah, I think that works. That looks like it's right to me, right? But I'm confined to the logic that I use here because that's me. But yeah. And essentially I say 1 over this is a constant value, so I just simplified this top part here. I don't really need to do that. This doesn't really do much. 2 to the k is and then I just simplified this 1 over whatever this is to that value, and then I said over 2 to the k. Sorry, over 2 to the k. 2 to the k approaches infinity. 1 comma whatever is a constant, so it approaches 0. Where does that come from? Just logic, just not logic, but like it's a feeling. That's a lot. That's a lot of this paper. It's a feeling. So you have so I do that and I get approaches 0, about 0, right? For n over 2 to the k, which is sound logic to me. I mean, if you have n and I evaluate n first, it's a constant 2 to the k, and then I have over 2 to the k. Even if I treated n as infinite and it was increasing kind of like a linear graph, I'd expect a linear graph to increase slower, kind of, or have a just grows less than a exponential graph. And that's to say that approaches 0, right? Just by intuition is what I'm feeling again. All right. And then I said, okay, if it's approaching 0, I can say r to the 0 minus 1. Again, don't know if we can do this, but r to the 0 minus 1. Remember that this n over 2 to the k I'm saying is approaching 0. Hence, this is approaching this part here in this specific purple colored bracket. This exponent here is approaching 0. And if that exponent is approaching 0, by saying minus 1, r to the 0 minus 1 is the same as 1 minus 1, which is the same as 0. So I got this as 0. We can see how this is messing up. This has made my entire first bracket completely redundant. It's done, right? The answer is 0. Really, for all series, the answer is 0. But we'll resolve that later on, hopefully. And then I say, yeah. Oh yeah, I'm evaluating the red bracket, so I'll just show you again. P to the k, you got r n over 2 to the k plus 1 dot 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 dot. This dot 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 is just me doing that with other parts. So before this would be n over 2 to the k minus 1, and then etc. minus 1 minus 1 minus 1 minus 1, and until we get to these first sets. This first set comes from that n over 2 that we saw up there. I'm not constantly going to be scrolling up and down, so it's quite difficult. Actually, let me see if I can do something quickly. Actually, I don't think I can do that. Yeah, I don't think I can do that. Okay. I'll see if I can do it here. Oh no, that's gonna mess up everything. Yeah, okay, let me leave that. The first term, so let's go here. So we have that comes from that leftover part, that red leftover part that I showed you. And we can see a pattern here. You have n over 2 to the k, n over 2 to the k minus 1, or n over 3 minus 1, 2 minus 1, which is 1, which is 2, just to preface that. So we can see a pattern of n over k minus 1. No, let me say r to the n over 2 to the k minus 1 plus 1 here. Right, we can see that pattern emerging from this. There's a pi, there's a large pi symbolizing multiplication of terms. So like you'd have sigma showing a summation of terms of a sequence, or a sequence. It's the same kind of thing here, but it's multiplication this time. That's it. So I say let us analyze the first bracket being this bracket here. And we say the first term of r to the n over 2 to the k as shown in the previous proof. So I'm talking about this here approaching 0. Talking about that. And I say this part is approaching 0 as established before. Established again. R to the 0 plus 1 is the same as 1 plus 1, which equals 2. Sure. And I say now taking the second, third, and fourth bracket will yield us values close to 2, as we will have the following. So you'll have, I don't really want to get into it, but each time you minus 1, you're going to get something very close to the answer. So you'll have 0.69, same spiel over and over again. So you get times 2 times 2 times 2, and obviously that may not be true for the first term, which it'll show later on. So over here you have r to the 1000 over 2 is equal to r to the 500 plus 1. Oh no, I explained it here. So I'm just gonna explain what I was saying there. So I have r to the n over 2 to the 1 here, 2 minus 1, whatever. It doesn't really matter that much. Plus 1, right? Say r was 5, right? N over 2 to the 1 of 5 is square root of 5. If I bring out my calc stands for calculator, by the way. Anyway, let me bring that out. Sorry for the under preparation. Okay. Yeah, that works perfectly. Alright, if I'm gonna use square root 5. So why is it not allowing me to? Okay. And then to the 1 over 2. Where's the over symbol? There. 1,49. Okay. That works around close to 2. It's not what I want, but if I say plus 1 here. Okay, it's just not working. 2,49. Quite close to 2. Here and there you might have things that might fix that. So if I have let me just say to the power of here as well. So we said that we defined this. Okay, yeah, the video cut out because my PC shut down. I have that automatically at 11:40. My laptop automatically turns off. It's to encourage me to sleep, but I decided to make a YouTube video. Anyway, let's get back. So we had, let me just put that back in. I actually think it's better I use Desmos. This is very slow. This is very slow. Alright. Yeah, I think that's gonna be way quicker. Alright. So you had 1,49353 whatever, and then plus 1 here. 2,49 whatever, right? And I say that, let me just go back down to where we were. Yeah, here. Okay. So say you had a bigger value. So our k value is this. It's actually here. This is our k value. This number that I'm changing. This is what our k value is. 1 over 2 to the whatever. 1 over 2 to the. I'm saying 1, but it could be anything. It could be term 500, 1,000, 700, a million. It could be anything. There's the n as well. So we have this structure. I'll just write it out so you can see r to the n over 2 to the k plus 1. I'm just feeling like my teacher. N over 2 to the k plus 1. So just so you can remember. So what happens when we have a large value of k? 2. See that? Approaching 2. What if you had a low value of n, right? So you had 2. Approach 2, sure. Or we had a large value, 2 as well. Okay, this is not a good example, but let's do this as well. Let's decrease this. I don't know. Okay. Because this would be some binary value. So it's actually not giving me the answer that I want. This is not good. This is the worst thing that could have happened. Because what I'm saying is right. That's the worst thing that could have happened. Okay, what about... Interesting. Okay. It seems what I'm saying computationally is right, but there was a thing in which, okay, we solved the problem together, it seems. I'm just gonna explain what I was saying because, it might still apply. Maybe I'm just not trying the right things out. So I was essentially saying if you have different variations of r, n, and k, which are 3 variables, r lesser variable, n lesser variable because it's more, it doesn't vary, it's something we set when you plug it into an equation. But there's still variables, I'll call them, right? As you vary these different variables, you might get something that's not 2. You might get 2,49, you might get 18, you might get 700 as your first term, not your last or anything, but your first term. So your first few terms might be not close to 2. They might be far from 2, far enough where you can't say they're 2. In these early terms, I'd like to call them, multiply out to get some value. I call that C, right? So you might have, for your first terms, it'll be 700, 400, 300, 200, 100, and then it jumps to 50, then 25, then 10, then 9, then 4, and we can see from this here, no matter what I do, you're approaching 2. If I remove this here, you're approaching 1, but that's not the point. This part approaches 1, this part is 1, so plus 1 is just 2 when you add them up. So we can see we're approaching 2, right? So I don't know why it's working now, but before there was scenarios in which I'd have an n, I'd have a k, and I'd have an r that in very specific manipulation of it makes it so that it doesn't approach 2 at the start, which it still doesn't. I still see some variance there. Wait, I said 0 to the what? Wait, what? Okay, we might not be able to trust Desmos. What the heck is going on here? Interesting. Okay, I might have to restart. I think Desmos was fried. Yeah, okay. I think it was here. Yeah. Oh no, the problem was Desmos. Yeah. That was the problem. Okay. Perfect example. Alright. You have R as 100, you have N as 1, you have a K. And the thing is, I'm setting K as a low value, but it should not be that. You can see that from most values of N. I wish I could, okay, let me just say times 10 to the 100. Okay, that doesn't do anything. But I can't trust Desmos as shown in the previous problem. I'm struggling to see how this is going to work. Undefined. Yeah, but yeah, that makes sense. Okay. I don't know what I just did before, but I didn't have oh, okay. Oh, there it was. Alright, that variation slightly wrong because K is infinite. By my definition, I've expanded it infinitely. But oh no, these are early terms. That's what I was getting to. The K, if the K is an early term, so K is 1, K is 2, K is 3, you're gonna have values like 4 over here, or 100 or 1120 as R. You'll get 18,83, some large values at your beginning. So you can see you're not going to get 2 at the start, which you have to account for. And then by saying, okay, over here, if you copy this, paste this here, make this 3, right? You're getting closer to 2, but you're not at 2, right? Yeah, sorry. Okay. See how I'm getting closer to 2 there. Let's jump to 6. Oh, that was 1. Let's jump to 6. 2,19, whatever, right? We're getting closer and closer and closer and closer to 2. We're approaching 2, but we're not at 2 at the start. We have 3 times 5 times 18. Some quick math here. 3 times what? 5 there. 270. We have 270 at the start. That's a value that we have to account for, a value that we have to take in consideration when we're doing this. And that value, I don't know when it starts. Well, at this point, I don't know it started. So we call that value C. It took a very long time to explain C. Okay. Might have to speed it up. Yeah. You see, as the values get bigger, values of K get bigger, we approach 2. But we don't know when K, what value that might be for anything, right? Okay. And getting broken, this part is really just explaining that I got 0 at the first part because it was R to the 0 minus 1, which is 1 minus 1, which is 0, which is not the best situation because you have 0 at your top part. 0 over R minus 1, whatever R would be, it's going to be 0. The answer for all series equations will be 0. So that obviously doesn't work, and that's telling me, I have to do something, and we get into breaking back. I say bracket 1, right? So we use this rule to get so we have over here indeterminate form. It means it converges to, it becomes 0. I don't know why I say indeterminate there, because 0 over something is not necessarily indeterminate. I think 0 over 0 is indeterminate, but whatever. The bottom part might not be 0, but it actually might. Well, you'll see. So I say the limit is k approaches infinity, r to the n over 2 to the k minus 1. And I'm just trying to remember what I was doing here again. Oh, I L'Hopital rule the whole thing, right? From k, I just looked at the limit of k. L'Hopital rule the whole spiel, the everything, right? Before there's only n over 2 to the k, now we're doing everything. No one's safe, right? You have the limit, not limit, you have r n over 2 to the k, right? Times the natural log of r times by 1 over 2 to the k ln2, which is this inside I evaluated. I L'Hopital rule the inside bracket here. And then plus 0, this plus 0 comes from the fact that minus 1 is a constant, so if you differentiate it, you're going to get 0. Could be minus 0, plus 0 is what I put there. Actually, I don't know if we can minus 0, plus 0, I was thinking with that. But yeah, then I just multiplied that out. I said r to the n over 2 to the k. What just happened? I said r to the n over 2 to the k times the natural log of r. I just simplified this to that. Okay, next bit. And then... Ooh. Oh yeah, okay. So instead of what I previously did, is I evaluated them separately, right? And the reason I L'Hopital rule here, the whole thing, was because some things approach 0 faster than other things approach 0, right? So say a linear graph and a exponential graph that is 1 over something, 1 over 3 or so something, that approaches 0 quickly relative to some other graph like a linear graph. I don't know how that would approach 0, but yeah, basically it approaches 0 very, very quickly. Things approach 0 at different rates, and saying that, okay, this is times 0, so it must be this approaches 0, so the whole equation, the whole top part of the whole numerator approaches 0. It might be incorrect because some things approach 0 slower than other things approach 0, so they won't have an effect on the rate of increase of the other graph, or the actual value of the other graph, because it's increasing so much. So by defining the numerator in terms of the rate of change, right, I can compare and multiply out the brackets, accounting for the fact that they increase at different rates by showing them with variables, right? So you have this part here, right? Now, where does the 2 to the k come from? Well, the 2 to the k comes from... I actually don't think I addressed that, did I? That's a bit odd. Oh, no, I didn't talk about it here, but I talked about it here. So we established previously, we're going back to these brackets where it's 2 times 2 times 2, etc., because it approaches 2, as I showed here. Going back there, just quickly glossing over, you have 2 times 2 times 2 to this times c being a constant of these first bigger terms, and we call it 2 to the k times c. All right. 2 to the k times c. So you have this part, which is our first bracket here, right? And these leftover brackets expressed as one thing, 2 to the k times c. Right. Multiply those out, and then you see the 2 to the k there, 2 to the k there, those cross cancel. Yeah, those cross cancel. Yes, Nathan? Yes, they do. Then you just simplify. There's just a bunch of simplification. You get this here. Sure, everyone's happy. I think, maybe. Alright, I'm just trying to see why I highlighted the time C. Okay, yeah, I don't know. Oh yeah, because it still comes from that part which is red. Yeah. Alright, and I just call this whole thing tx. This whole thing, I mean. So this top part, this numerator here, not excluding r minus 1. And I say Sn is equal to tx over r minus 1. And then I do the same thing, as you can see before, difference of two squares, r to the 1 over 2 minus 1, r to the 1 over 2 plus 1. I do that repeatedly like last time. And now I call that thing ak. Before it was pk, remember. Now the denominator multiplied values are called they're called pk. So now we're just talking about this part here when I reference ak, sorry, ak for the denominator. I do that here, and then I'm evaluating this orange part first, just like last time. And we do the same type of thing, but now with the new knowledge that we got, we evaluate the whole thing, and we get to this. So I L'Hopital rule this part here. You have r to the 1 over 2 to the k, which is the same as 2 to the minus k. I don't know, I really like that this time, but yeah, it's the same thing. R to the 1 over 2 to the k times ln r times 2 minus k, which is the same as 1 over 2 to the k, times the natural log of 2 times -1. The -1 coming from the fact that, trying to remember this, because before you'd have 1 over 2 to the k, and then you'd have to differentiate it, and when you did that, you'd get some weird, well, not weird value. It's just a simplification of what I did last time, because now I have 2 to the minus 1 k. So now the derivative of minus k being the variable that we're evaluating, is going to be -1. And then minus r to the 1 over 2 to the k times the natural log of r times the natural log of 2, that coming from this, over 2 to the k, which is this 2 to the k here. So you have this here, this negative being there. Alright, and then we will reapply the same technique using bracket 2 being red. Remember last time we colored it red for the leftover parts of pk, as we called it before. We do that to the denominator bracket 2, kind of. We'll call that bracket 2, classify them as bracket 2, brackets 2, but yeah. So yeah, we do the same thing. We can see, I'll just show it again. So now we, instead of having n, because now we're talking about an actual constant 1, we don't have to think about what n could be. You can just say it's 1. So it actually, the same concept applies at the bottom. It's actually, we have already gotten written out, so you don't have to show it again. This is actually what it's meant to, because this n could be anything. It could be 100,000. Oh, maybe not. That's odd, undefined. Let me think quickly. Times 10 to the 31. Very large value. Oh no, but Oh, x could be undefined. This could be so huge that it's undefined. Wait, 1000 over 2 to the 4. It's 2 to the 4. That's interesting. 2 to the 4. That's 16. 1000 over 16. Oh, yeah, it's just very big, I think. It's just saying what it's saying. But, okay. Just to check the time. Yeah, it's a long video. Apologies. Yeah, so we're here. We are on page 15. So we're speeding past it quite quickly. Yes. Yeah, I said we apply the same concept. We said it's approaching 2, so there's times 2, and these would have some larger values we called C last time, but we're going to call it X because now we have a definite one, whereas before we had N over at the top, so it wouldn't be exactly the same values. Now, before we had r to the n over 2 to the r to the n over 2, and that can be written as r to the 1 over 2 to the n. This can be okay. I'll just show that here. Sorry, I'm reading this as well. Also, if you want to look at this video, it would probably not this video, this report or this thing yourself for help to help me. It would be in the description. Hopefully, I won't forget it. It will be in the description for you to use. Oh yeah, I'm trying to define when the I remember now. Okay. So say we have values. We have one. We have an n value, right? And now the problem with n is that I don't know what the value of n could be. You could pick anything as your n value, you know. So I'm trying to remember the name for it. Your C could change. So your constant could change at a certain point. You don't know what point it's gonna change. So over here, it happened to change at 2 to the 6. But say you had a smaller value. Say you had R and you had this. Sorry, it's taking long. 11,422. We got close to 2 very quickly. Essentially, the premise of it all is you don't know when you're gonna approach 2. When 2 is like when you're around about 2, it's not that big of a difference for you to not call it 2. You don't know when that is. And essentially, I hope to establish that the reason it's 2 is because it's 1 plus 1. So what we're actually talking about is r to the n over 2 to the k being 1, right? Approaching 1. So if I remove this, that shines light on what I wanted to show much better, much clearer. Yeah. You have 10, 3, 1, 1. Or 10, 3, 1, we approach 1 quite quickly, right? We go from 10 to 3 to 1 to 1. We don't know, depending on your value, the rate is at which you approach this value here, 1, is very different, right? But we got to determine when around we're at like 1, right? So I say r to the n over 2 to the k is about 1. So r to the 0 is, so we're saying that n over 2 to the k is about 0, right? For it to be about 1, right? So n over 2 to the k is about 0 here. I'm saying, okay, now how do I write this out? What am I trying to show? Well, what would make n over 2 to the k approach 0? That would be n is less than 2 to the k by a significant amount. So k is greater than log 2n. Where does log 2n come from? I'm trying to figure that out. Yeah, 2 to the k is greater than or equal to n. Is just the condition for it. It's actually not the condition in my mind right now. If n is fairly small and 2 to the k is fairly big, then you approach 0 fairly quickly. So it would depend on your n. It would really depend on your n. But I know that n over 2 to the k approaches 0. So that means 2 to the k is greater than or equal to n. So when it's equal to n, then I know that, oh no, yeah. If 2 to the k is equal to n, then it's definitely gonna be 1 there. I mean, it's gonna be n over n, so it's gonna be 1. We don't want r to the 1, we want something greater than. So it's actually, I would take this equal to away, but r is yeah, I wouldn't say equal to there. I'll remove that. And then I subsequently remove k there, I mean the equal to sign there, but never mind that. Inversely, we will yield the condition for every term, hence the values for v. So where does v come from? V is just the point at which the early terms end, right? So over here I have k less than, so initially I had k greater than or equal to log 2n, because 2 to the k is greater than or equal to n, right? That's the point where it approaches 0, so k is greater than or equal to log 2n. And then I say inversely we'll yield the same conditions for early terms, conditions for v. So this is when the late terms start. These are the values for k for which the late terms start, and these are the values for k where the early terms start, because this n is greater than this value 2 to the k here. And I have k is less than log 2n, or could be written as v is between 1 to log 2n. Because v is an early term value, so it must start at 1, because k, well, it could actually be anything between 1 and whatever, but I chose it as 1. It doesn't really have to be an integer, but we defined it as integers just for ease of use. So it's between 1 and log 2n, sure. Log 2n doesn't have to be, so I would say this could be anything, but okay. Bracket 2 is the numerator to the early terms. Okay, so now we're just talking about early terms. N over 2 to the e, n over 2 to the e, n over 2 to the e, yeah. So this equals c. We defined this point as our early terms in the numerator part. And then we define this in the denominator. You have this okay. So bracket 2 in the denominator, including early terms. I remember that v that you saw before, I swapped it for e, just for simplicity, which is a problem with this document. Also probably a detriment to my around like not coming anything in the Tom Rocks maths essay. Changing variables, unsure of definitions, etc., etc. But this is a long video, isn't it? Yep, it is a very long video. All right, you have these early terms here. This is for the denominator, right? So the thing we're just talking about. And I'm gonna say this part here is our denominator, early terms. You can see that this is 2 the n over 2 to the whatever. I'm trying to see why I said this. So what we said, x, yeah, I'm sorry, I'm figuring this out with you. I said x was this, right? These early terms, right? But this is defined as 1. So n could be anything there. So that is fairly... And then I defined at which point k approaches, what's it called? At which point k makes the equation of r to the n over 2 to the k, or the term r to the n over 2 to the k approach 1. Okay, so I think it's starting to build up in my head a little bit. But there's a conceptual error because I'm defining 1 and then I'm defining... okay. Never mind that. You have... these early terms, right? Yeah, this is very scrappy of me. I don't know if I can do this. Over here, essentially what I was trying to do, I don't know if it applies, maybe I just can't think of why it works this time. But essentially what I was trying to do is like, okay, this k, no, I didn't write it out there, I wrote it out somewhere else. I didn't write it somewhere, no I did, but I just can't find it. Okay. But I was trying to define x in terms of c. I know that c and x might be different because n might be big and r might not be big. I mean, n might be big and 1 is not big and 1 is, it's a constant. N over 2 to the e, 1 over 2 to the e, 1 over 2 to 2, 1 over... These are the early terms of the denominator. These are, because over here I'm saying this is the same as 2 to the n minus 1, which is 1 over n. When you say times 1 over n here, the n cancels here. But, and then I'm saying the plus 1 is 1 over n, which doesn't matter what it is, 1 is, it's going to be 1. So that's square root of 1 or 1 over 6, or to the 1 over 6. It doesn't really matter, it's going to be 1. But there's a conceptual error. If it's 1 over 1 squared, if it's 1 squared, it might be very different. Might give me a different thing. Anyway, let's continue. C to the n minus 1 is what I put at the denominator, and I represented x in terms of that. very scrappy work. Alright, 2 to the k times c to the n minus 1. The 2 to the k, we're still talking about bracket 2 here. Bracket 2 still has 2 times 2 times 2, etc. Right? Because 1 over 2 to the k converges, it converges to 0 there. And then you have the r to the 0, and that becomes 1. 1 plus 1, 2, 2 times 2 times 2 repeats. Fine. It's this part which is a bit suspect, but whatever. It's a bit late, so I'm trying to finish this. Yeah, so AK we defined before as, the product of the top or of the, of the denominator. Okay. Yeah, so bringing it all together, AK is this part here. We haven't seen that in a while, so let me just bring it back up very, very quickly. It comes from us applying that rule to this, remember. Alright, these 2 to the k's cancel again. You get this thing here. The c to the n minus 1 is the glaring problem that's staring at me right now. Bringing it together, a times r to the n over 2 to the k times the natural log of r times c over the natural log of 2 over minus r to the 1 over 2 to the k times the natural log of r times the natural log of 2 times t to the n minus 1. Where does that come from? This comes from k, which we defined as the denominator part multiplying together. So that comes from this. That we defined earlier as, I think, tx. Or tk, probably tx, I think. And then we multiplied everything here. So this is over. Wait a minute. A times this times where did this go? What am I evaluating right now? Oh, I moved that up there. Sorry for that delay. I'll move this up here because it's a fraction like this. Yeah, and I multiply those out, and I said what? RT then over 2 to the k, so this times c. So I multiply these c's together. This adds 1, so it's 1 minus 1 over n. I just turn this into 1 over n there. This natural log of r squared comes from this, which actually, now that I know more about the natural log of, I could say, because this is everything squared, all squared. So I'm thinking I could move that and make this two natural log of r. Anyway, leave it. R to the 1 over 2 to the k times r to the 1 over 2 to the k there. That comes from these. Negative comes from there. And then I multiply these two together. I added these. I multiplied them, so I added them together. So you got n plus 1 over 2 to the k because it's multiplication rules of exponents. That there. I just made this, gave it a common denominator of n. This became times n minus 1 over n. There. Yeah. This n plus 1 over 2 to the k becomes 0 because inshallah. Or, well, let me not say that. Sorry, apologies. N plus 1 over 2 to the k. N plus 1 is a linear number, linear value, or linear graph, if you like to call it that, over 2 to the k, which is an exponential graph. We intuitively know that exponential graph should grow faster than any n or linear graph. And because we've evaluated k first, n is a fixed value anyway, so we know that it's going to approach 0 in any case. It becomes r to the 0 times the natural log of r squared c to the n minus 1 over n. And this is 1, the same as 1, so it cancels. Minus a times the natural log of r squared over c to the n minus 1 over, yeah. So this is the final thing we have, I think. Now, I don't know where my pictures went. That's interesting. Quite interesting. If you don't mind, I'm gonna go to Word. If Word would open, stop jumping around. Thank you. Alright. Tom Rocks Maths. With the addition of Claude, I should have asked it to help me as well. See what's wrong with my thing. This wasn't out when I made this document, as you can see by the scrappy mathematics in this essay. Alright, there it is. Okay, I don't want to do that. I want to zoom in. How do I do that? I feel like a teacher. Alright, I can't do that. Oh no, I can. Oh, there you are. Beautiful. Alright. So what was I doing here? I got a model to CSN versus N. Okay, so I'll show you. Alright. So we simplified the series equation to this value. Oh, not value, variables. C, don't know what C is. But we define C as, it can be anything, right? We define C as stopping at some point. Right, it'll change depending on your number. Now, how did we determine C again? We said C is where K is greater than or equal to is less than, actually. That's for the late terms. K is less than log n base 2. I think. Yeah. Log n base 2. So when k is less than that. So we plotted here. We have Sn, and you have the series n versus n graph. Essentially what I did here, from what I did, is I looked at the broken formula that I got, and I tried to determine Sn versus n by, I'll show you here. I remember me trying, because we have C here, we have R, and we have A. Now, what did this do? It did nothing. We literally just broke the equation, and not in the good kind of break, just broke it straight up. Yeah, so I kind of manipulated this to see what the C value is for each one, and then compare that because the C value would stay constant kind of for most values. It would increase. I remember it increased in certain squared increments. But yeah, we did that, and I tried to calculate the C value. The SN part I'm trying to see. Yeah, so here I just kind of admitted defeat, I remember. I just want to see what... Yeah, so I calculated C for each one. I don't want to see like stayed however at a certain value. This graph does not make much sense to me. Yeah, I plotted it. I saw it didn't work because this is just I don't know what's going on. This part I really can't explain to you that easily. Yeah, but I think I was plotting what the series of each n would be versus n. So at 1 you'd have this, and at 2 you'd have this, and then I compared that to the actual C, and it just was not the actual C, the actual series value, and it was completely off. You can see you got like a scribble, it's just playing around with me a little bit, shaking me up a little bit, wasting my time a little bit. Anyway, we got that, and we had a conclusion, which was half done because there was no time to do it. I didn't have time to complete my essay, but it was quite an interesting essay. I don't know why this is just not scrolling. Okay, just do whatever you want. Yeah, just do whatever you want. Yeah, but that, in conclusion, that's my essay. Let me just... Yeah, in conclusion, that's my essay, right? If you have any comments, solutions, or critiques, or just a way to murder my ego as a mathematician, please drop any comments you have, drop any suggestions. I'll be reading the comments if there are any. Probably just going to be lingering on the YouTube algorithm for eternity, but hopefully we can get help from anyone willing to help me with this. Yeah, that's all I have to say. Should I do the PewDiePie thing? I'm gonna try to do the PewDiePie thing. No, I'm not gonna do that. Bye bye, I guess.